Hello. It's the 14th of August, 2015. This is episode 19 of the Unseen Podcast. And this is your host, Paul Carr. With me tonight is Adam Synergy Smith.
Hey, Paul. Well, hello from the 15th of August.
Yeah. Now, Adam, I should point out, Adam is up at a ridiculous hour in the UK just to do this podcast. We appreciate that. This podcast is an unscripted, unedited, open participation Creative Commons podcast. If you want to know more about this podcast and the other 18 episodes, go to unseenpodcast.com. You can also find us on iTunes and other popular subscription services. Now, Adam, earlier on, you pointed out to me there's some interesting news about exoplanets. So let's talk about exoplanets.
Yeah.
Tell me what this paper is about. It's pretty interesting.
There's a paper that was submitted on the 10th of August, the astrophysical journey, I think, about WASP-47, the WASP-47 system. And they've looked at some new data from the Kepler K2 mission, which is the mission that's going on at the moment, using the Kepler spacecraft balancing its only two remaining reaction wheels.
Right.
Tricky business. But
Yeah.
they're managing to do some useful science. And they've looked at the WASP-47 system that had a previously known about hot Jupiter planet, a big Jupiter-sized, Jupiter mass planet very close in to its star, and they've found two new planets, a Neptune-sized outer planet and a super-Earth inner companion, which is very interesting because the inner companion has managed to stay in the system while this huge Jupiter mass planet has migrated inward, or it's migrated in with it. But it's the first one we've found. We've found lots of hot Jupiters, but we've not found one that's got another planet with it. This is the first one. Found by looking at transit timing variations, which is also something new.
Right. Now, let's explain what transit timing variations are.
Well, a transit is when an astronomer sees a planet move across the face of the star from our point of view. And when it does that, there's a tiny little dip in the amount of light that we can measure coming from the star. Flux, what astronomers call it. They measure the flux, and you get a very characteristic dip in the amount of flux coming from the star that tells us that a planet has moved across the face of the star. So these transits are often very regular. We know another way that we know a planet is there is because if it's on a 4-day orbit, it will see a transit every 4 days. If it's on a 400-day orbit, we'll see the transit every 400 days. But occasionally, these transits aren't that regular. They're off by a tiny, tiny amount. Either planet arrives slightly early or it arrives slightly late. And that is usually because of the influence of another planet that's exerting a gravitational tug on the planet, either slowing it down or speeding it up. And if we see enough of these transit timing variations, scientists can do some very difficult calculations and work out the size, mass, and orbital characteristics of the other planet. And that's what they've managed to do in this case. They've found two new planets, which is very impressive. Very impressive. Not an easy task at all.
Now, do these new planets, they transit as well? They transit, don't they? They pass in front between the star and the Kepler telescope.
They do, yeah.
And but they're smaller planets.
They're
Yeah.
much smaller, yeah.
Now, what interested me about this paper, and I have to admit, I just had a few minutes to look at it, was that the sorry, we have a bit of noise here. We'll let that pass. Okay, thank you. And
My computer, sorry.
that's okay. It's unedited podcast, so we sometimes get these little glitches. The inner planet. We should point out this star is almost exactly identical to the sun, to our sun. It's only slightly more massive and about the same radius and everything. But there's a planet, this inner planet, which is described as something about the size of Neptune, is orbiting its star every 19 hours, which is
0.79 days.
Which is that means it's really, really close to the star. And
hang on, sorry.
So anyway, as you can tell, we didn't rehearse this.
Sorry, my computer's doing something strange.
Well, your sound is coming through. Okay, just fine.
What's 47? Yeah, the hot Jupiter, what's 47b, is on just over a 4-day orbit. There's a Neptune-sized planet on a 9-day orbit, what's 47d, and the super Earth is on a 0.79-day period.
Okay, it's a super Earth that's in close. Okay, yeah.
Yeah.
Now that is really, really close. They all are, but that one must be boiling.
The super Earth inside the orbit of the hot Jupiter. I mean, if it's hot on that planet, it's got to be, literally boiling on the super Earth.
Yeah, they give a table at the end of the paper that shows the radii and so forth.
It's called a super Earth, but I mean, it's not going to be anything like Earth at all. It'll be a ball of hot gas, I would imagine,
or molten rock or something.
Yeah, more likely.
Like, and it's hard. It's hard. What's hard for me is to imagine how it could survive for any length of time. It must be getting blasted off into space.
Yeah, they have found similar planets. I think the first terrestrial planet that was ever found was a super Mercury, molten planet, quite close in. I mean, that's ridiculously close.
Yeah,
zooming around a star in less than a day.
Now, if our solar system was like that one, there would be no life anywhere.
No.
It's interesting to ask, and I think a lot there's a topic of active research is why some solar systems the planets migrate inward so they're basically uninhabitable, and others do not. In our case, we think Jupiter may have migrated in about halfway and then went back out.
Largely due to the tug of Saturn and Uranus and Neptune.
So it has a lot to do with the sort of the initial conditions that you begin with.
It's the roll of the dice, isn't it?
Yeah. If your dust cloud or whatever, your gas cloud is a certain shape and size and angular momentum, you'll end up more like us, and if not, you'll end up more like this WASP 47 system, which very cleverly been teased apart by the Kepler 2 project, which is, as you pointed out, Kepler 2 is now looking really promising. There's been all kinds of discoveries, and when people were ready to write it off a couple of years ago, they've
done a wonderful job in keeping it going. You know, usually when a spacecraft loses 2 of its reaction wheels and it's only got 2 left, they would give up on it and decommission it. I think they've done a marvelous job.
Well, yes, that's actually true. They probably would in many cases.
Yeah.
But they found a way to keep the telescope lined up well enough.
That's a tribute to the marvelous science that the Kepler Space Telescope has done.
Yeah. Well, it's a great instrument. That's the main thing. It's a shame to waste it. Yeah.
Thousands of planets. Discovered more planets than any other single instrument. That's for sure.
Now, if you're not familiar with exoplanet hunting, you have to know that there's a few different ways that we find exoplanets, but this particular way, the plane of the planet as it's orbiting its star has to be kind of edge on to the line of sight.
Yeah.
So we can't see them all. We can only see that small subset.
Quite a small percentage of those planets that are out there.
So there's more of so it's basically a statistical exercise. We know that there are more of them out there, many more, and we assume, and I think it's a pretty good assumption, that it doesn't matter how they're oriented, they'd be the same kind of planets. And since there's nothing special about the line of sight to Earth, so at least we think that's a good assumption. I'm pretty sure it is. But and so what the whole Kepler mission is about, it's not so much about finding all the exoplanets, it's about finding the typical exoplanets and
a characteristic sample.
Yeah, a sample.
Yeah.
And you assume that the sample will be that the whole population should be similar to the sample. Which
yes, but I think one of the things they have found is the incredible diversity of planets that are out there.
Yeah, and planetary systems.
20 years ago, we had no idea that we would find super Earths, hot Jupiters, giant planets.
Yeah,
people have speculated, but we really didn't know what we would find.
The hot Jupiters were the first things we found, right? Because they were easy to find. Because they're close to their star and they're big, and
but at the time they were predicted not to exist.
Right. Nobody. And now they think they kind of understand how that works.
Yeah. Well, obviously they form further out. They must form further out.
They have to. Yeah.
It's not cold enough for gas giants to form that close in, so they must migrate in. And they seem to do that very quickly, quite early on in a planetary system's history.
Yeah, in the first few million years, which is a blink of an eye on that time scale.
I think as we discover the characteristics more and more systems, we'll have a good idea of the proportion of hot Jupiter systems there are compared to different types of system, like our own solar system. There's a bit of a bias at the moment. We discover more hot Jupiters, as you say, because they're easier to find. So we've found a lot of them. That doesn't mean that most planetary systems contain hot Jupiters.
Right. Well, one of my hopes for the James Webb Space Telescope, with its very good infrared resolution and light gathering capability, we'll be able to catch some of these things in the act as they're becoming hot Jupiters.
Well, there's been a planet discovered. Well, that it was actually imaged last December by the Gemini team in Chile, using the Gemini Planet Imager. Have you heard about that? 51 Eridani B.
Yes, I have heard about that. In fact, I sent a small amount of money to the SETI Institute, so they gave me a little heads up on it.
All right. Yeah, they've managed to directly image it, haven't they?
Yeah, I think,
which is another very impressive feat.
Yeah, this was, I think, Frank Marquis, one of the people at the SETI Institute, who was one of the leads in that.
It's a big team of people. I think there are about 50 astronomers working on the project.
Right.
But they found a 20 million year old Jupiter-like planet in a very, very young. No, I'm not sure it's 20 million years old or 2 million years old. Actually, I have to check that. It's very young, anyway. Young Jupiter.
Yeah, I'm sorry. I just read the press release. I didn't read the paper, but And of course, as we've talked about before, press releases are could be a little bit oversimplified.
Not only have they imaged it, but they've managed to conduct spectroscopy.
Yeah.
Where they've split the light coming from this planet. It is got quite a high luminosity. So they've been able to look at the spectrum of the planet and find methane and water vapor signatures coming from it.
Yeah. Now, before we go much further, let me introduce Ciro Vila.
Hey, Paul. How are you?
Can you hear me? Yes, I can hear you just fine.
Very good. Thank you.
Hi, Ciro.
Hey, Adam. How are you?
I'm very well, thank you.
Yeah, this time of year, it's hard to get a panel together. People are all out enjoying their last days of summer.
Sorry for joining a bit late, but I figured better late than never.
Yeah. No, we don't. We're on an exoplanet thing tonight.
Very nice.
We'll see where that takes us. But Adam introduced me to a recent paper about the WASP 47 system, and then now we're onto the new discovery using the Gemini.
Right.
Adam, tell me what you know about the Gemini imager.
The Gemini imager is an advanced adaptive optics coronagraph, which means that they use a coronagraph to block out the light of the star. Basically, they mask it off with a big black circle. And it's a ground-based telescope based in the Atacama Desert in Chile. And they use a system of adaptive optics to account for the water vapor, mainly, in our atmosphere that can mess about with their imaging system. It corrects the light coming from a star or a planet to account for disruption of the signal by stuff in our atmosphere. Very clever piece of kit. So
yeah.
They found this star. Horrible. Oh my God. Crazy. I think a small piece of plastic.
I thought that was just applause.
Yeah, anyway, so this.
Oh, we lost you, Adam.
No, it sounds like a
Oh, he's back. He's back. Okay, we lost you for a second there, Adam.
Sorry. 51 Eridani b. It's a Jupiter-like planet in a 20-million-year-old star system, so very, very young. And it has a projected separation from its star of 13 astronomical units, 13 times this from Earth to the Sun.
So it's still fairly far out. Yeah. Okay.
Yeah, it's further out than our Jupiter. But then, as we said earlier, these planets have a habit of migrating inward. So it may move. It could move in to become a hot Jupiter. It could move in only a little bit to become like our Jupiter. It's very early in its history, yeah.
Yeah, we only have to wait a few million more years, and we'll know.
Well, yeah.
Which
yeah.
And yeah, well, I mean, I'll bet there's a way to determine if it's migrating in or not, without waiting several million years to find out.
They've looked at this planet with their adaptive optics coronagraph, and they can tell it's very red, indicating a cloudy atmosphere, possibly reminiscent of brown dwarf. Their spectrum is very similar to that bigger brown dwarf star. And they detected methane absorption features very prominently in its spectra, and also hints water vapor, which is impressive, very impressive feat. Be able to look at a planet a few hundred light years away. I'm not sure of the exact distance, I don't think it is a few hundred, actually. It's nearer than that. Not sure. I'd have to look it up.
Well, this is a naked eye star, so it's probably within a few hundred light years.
Yeah, I think it's more like 20 light years away.
Okay, yeah. And most of the stars we can see with the naked eye are not that far.
Oh, and it's also in 51 Eridani of the hierarchy. It's part of a hierarchical triple star system.
51 Eridanus B is about 100 light years.
Right. Yeah.
That, I don't know if that's what the question was, but it's about 100 light years.
Yeah, okay, right. That makes sense. But still, that's he's right. That picking apart the spectrum of that thing with from almost any distance is a feat, and it bodes well for the future. I think we can do that with existing instruments.
Yeah, it's the first new exoplanet that's been discovered by the Gemini Planet Imager as well. The first one that they've discovered, rather than they've found planets before, but they've looked at planets that have already been found by other methods to confirm that they're there. This is the first one that they've found independently. So that's good news for the future. First of many, I would hope.
Yeah.
They're not going to be able to find small Earth-sized planets because they're far too small.
I mean, with this instrument, yeah. I mean, there is a way to do it, but it's been canceled. It was called the Terrestrial Planet Finder.
Yeah.
And it was unfortunately the James Webb Space Telescope ate all the money.
Yeah.
But of course, now James Webb can hopefully make up for that by.
James Webb should be able to perform some pretty useful spectroscopy of planet atmospheres. That's what it's going to be good for.
Yeah. It won't have the occluding disk, but there might be a way to figure that out. But the Terrestrial Planet Finder, the idea was to put the occluding disk or whatever it was a long way away.
The coronagraph, yeah.
Yeah, and so block the star exquisitely. And
it's a good idea, yeah.
And the only way we have to do that right now is when something like an asteroid passes in front of the star. But then we only have seconds, so we can't really get a good spectrum or anything like that. But
no, you'd need to look at it for considerably longer.
Yeah.
To get much meaningful spectroscopic data at the moment, anyway.
Right. So hopefully something like the TPF will be revived in the future.
I would hope so.
Okay, let me we have a little pause here. I have an echo. But let me introduce Patrick Festa.
Hi, my apologies for being so late. I was taking a nap and didn't quite get up in time. Sorry about that.
Well, the way that works, Patrick, is just I'm still taking a nap, so just keep on going. All right. So anyway, Patrick, we've been talking about exoplanets, and Adam's been doing some fair bit of reading on that lately. Now, let's sort of think about where that's going. The exoplanet, we're finding a lot more exoplanets, and K2 is finding exoplanets. And not only that, but we're starting to get some idea what they're made of, at least in the bit larger ones. In the long-term future, we'd like to get, the dream is to image and get spectral data on terrestrial planets. Hopefully terrestrial planets around sun-like stars. But how far away are we from that? We're pretty far, huh?
Yes, at the moment. I mean, it's been likened to trying to look at a firefly next to a searchlight. Now, it's a fairly good analogy. Very, very difficult when you've got a star of such high luminosity burning away. next to a tiny little planet. So the idea of flying a coronagraph out in space probably going to be the solution.
Mm-hmm.
But it's going to be down to either NASA or the European Space Agency, or maybe one of the new spacefaring nations to do it. And there are no plans on the table as yet to do that.
Right. Well, there were, but the funding's been withdrawn.
Yeah.
And there are other worthwhile things that have also gone begging for money. So, like, I don't know if you know about LISA, which was the
LISA Pathfinder, yeah.
Yeah, well, there's the Europeans have continued working on LISA, but the U.S. funding was withdrawn.
Yeah,
about 3 years ago, and the idea with LISA would be very long wavelength gravity wave detection.
That's right.
And really trying to look as deep into the origins of the universe as we possibly could, and that. I know a lot of people are very enthusiastic about that, and Michio Kaku used to talk about it all the time.
Yeah,
and it may still happen, but it'll probably be a European mission, not a.
It's the one big aspect of Einstein's theory of relativity that remains to be tested.
Yeah. Now, my understanding is that there's a lot of optimism about finding gravity waves with LIGO.
That's right. I think that's a big reason why funding for LISA was withdrawn, because the LIGO team are getting closer and closer.
Yeah.
So
but the thing is, LIGO is a much shorter baseline, so it cannot see the really long wavelength waves from the Big Bang. It can see astrophysical events, like the merger of a black hole and a neutron star or something like that. They are expecting to get, after many improvements to LIGO, to see some astrophysical events in the next year or two.
It's taken them a long time because it's difficult business.
It's an incredibly
ruling out all the terrestrial influences on their equipment.
It's an extremely sensitive instrument. So it sees everything. It sees all the noise, and it sees trucks driving by on the highway 5 miles away. But what they've done is they have one in Louisiana and one in, I believe it's Washington State. And they won't declare it a real event unless they see it on both instruments. What LIGO does is it shoots lasers in two different directions, right? And the idea is that when the laser light comes back together, it interferes, and so you can measure the difference in phase between those two, that original laser, and figure out how far the laser has traveled in each direction, and then a gravity wave should change that phase, cause it to oscillate. But then again, so should almost any other vibration you sense. In the ground.
They have to spend something like 10 years characterizing all the different terrestrial events, earthquakes, aircraft flying by, all sorts of things.
Yeah, it's buried underground to try to keep the ordinary noises out, but it is really, really difficult solution. But they think they've got it. They think they've got. So we'll see. It's an extremely difficult measurement to make because gravity waves are very weak, very, very weak.
I would imagine they're up for a Nobel Prize if they can do it.
I think so. I think first time they get a confirmation of an astrophysical event, it's going to be like, for example, if you see it on both instruments, and then you look out in your telescope and you see it, that.
Yeah, that's what it's going to take, but it's doable.
It is doable, and there's a lot of good reasons to believe that gravity waves are there, but
Einstein's been right about everything else.
Yeah, well, not only that, but we see the kinds of systems that should be generating gravity waves, and they are losing energy. And the only place we know the energy can go is into gravity waves. So,
Yeah.
There's other reasons why we think the gravity waves are there. And as you pointed out, the general theory of relativity, which predicts them, is extremely well verified in every other sense. So we do it. And actually, when Ben Tippett was on in episode 1, he mentioned he was optimistic about that. So let's hope so. And that would be when LIGO gets a hit, it will open a completely new era of astronomy. Gravity wave astronomy will be new, and I think it will probably give a lot of. I think instead of discouraging something like Lisa, it will actually encourage it. And
yeah, I'd be interesting to hear what Pamela Gay's got to say next week, because she's at the IAU meeting this week and next week. It'd be interesting to see her opinion on what's big, what the big news is in astronomy. There are new areas opening up. There's gravity waves, neutrino telescopes. That's looking promising. Looking at physical neutrinos from.
Well, these really high energy neutrinos that they're detecting now are thought to come from the same place as cosmic rays, but they can't
and
really
dark matter as well. I mean, the detection of dark matter is still to be achieved. Where's that going at the moment? I'd like to hear what she's got to say, because I think there are probably people are getting tired of not finding dark matter. It's getting embarrassing.
Well, it took many, many years to figure out the solar neutrino problem. So it's going to take, I think, many, many more years to figure out the dark matter. And if dark matter may not be what everybody thinks it is, it may turn out to be something different.
I have a hunch it's probably more than one thing. It could be a combination of, who knows, 3 or 4 different things.
Yeah, we kind of know that it's a cold thing, and that it doesn't fly around the speed of light. It tends to be have mass, and
it's
so
likely to be a subatomic particle of some form.
I think it'd be interesting if it turned out to be a particle that no one's predicted. Because I mean, let's face it, it is the biggest challenge. One of the biggest challenges to physics right now is we don't know what dark matter is.
Or dark energy.
Well, dark energy, I think some physicists will tell you, "Oh, don't worry about that." We got to figure out dark matter first, and then we'll worry about dark energy. And dark energy is certainly something that we can, that we can observe unambiguously. There's no question that's what we're seeing, but nobody knows what it is. And some people say, I've heard Sean Carroll say a couple times, it's just a cosmological constant. Which might be the right answer.
Why not?
But nobody can calculate. But nobody can calculate the vacuum energy anywhere close to it. So, how did it get to be there? What is it? Why is it what it is? Something that we could be thinking about for a long time.
Negative energy is a crazy concept.
Yeah. And it's, it's probably, we probably haven't thought of the right answer for it yet. That may be the next generation or two.
It's not a bad thing, is it? Not to know all the answers.
Yeah. And I kind of actually take comfort in the thought that, the young scientists who figure it out probably haven't been born yet.
No, probably not.
And or may have just been born. So that's that remains to be seen. And dark matter, though, I think I agree with you. I think that we're going to at least make some progress in figuring out what it's not. over the next 15, 20 years, we'll have a lot more information about that.
I think the universe can be full of surprises, can't it? It's not necessarily the thing that we imagine it's most likely to be. There's no reason why it should be. It could be anything.
Yeah. Well, I mean, I don't think it's magic.
No.
Although I could be wrong,
You never know.
I could be wrong. I don't think it's leprechauns, but
It could be a cosmic joke.
You know,
it's difficult to it's difficult to identify the nature of something that cannot be seen. That's one of the difficulties.
Well, a lot of these things we can't see. We can't see neutrinos either, but we know they're there,
right?
From lots of exquisitely careful experiments, but it's
not. I mean, it's not an easy thing. I mean, obviously, we know that neutrinos are also created by the Earth. That's actually one of the. There was an article a few days ago about the detection of neutrinos in the Earth crust.
Yeah, that was clever. I can't remember all the details of how they did it, but separating those
out.
It was
the first time that they detected the neutrino in that coming from that particular region of the Earth. I think that they knew that found previously that neutrino was generated, from emanating from inside the Earth already, but not, I believe, not from the crust itself.
Yeah, well, we kind of, we'd expect them to be coming from there, but the tricky part is telling them apart from other neutrinos.
Yeah.
But it took many years of trying to measure, the solar neutrinos and finding that they weren't there in the numbers we thought they should have been.
Right.
But that developed an exquisite ability to determine the statistics of neutrinos, and we've since learned that the reason they're not there is because they have a little bit of mass, and they do change form as they move from the sun to the Earth, and that threw a curveball at the physicists, but they figured it out, and now they know that that neutrinos can change, which is all part of the standard model now. But at the time, it was rather bothersome for them, and so now we have, as we mentioned, we have neutrino astronomy that is really, I wouldn't say it's in its infancy, but it's still maturing. It's a very difficult thing. Neutrinos are very difficult to detect because they have such a low cross section.
They're called Cherenkov telescopes, aren't they?
Yeah. Well, the latest telescopes can actually, they have all the detectors set up, and they can sort of determine the direction a neutrino is coming from, which is very clever.
That's right.
It takes a lot of these massive tubs of, well, not tubs, but these massive lakes and so forth of water and materials, detectors.
The Cherenkov telescopes look for a tiny little blue flash of light.
Right.
Because the tau neutrino converts into a tau lepton, I believe, and it gives off a small blue flash of light, which can be seen clearly in water. So a lot of these telescopes, strangely, are located underwater or under ice. There's one at the South Pole, which I think is under ice.
Yeah, I think the South Pole one is the best one we have, I believe.
Yeah.
Is that the one that they underground water tank that they discovered the neutrinos after supernova 1987A?
That's right. Yeah. It's Ice Cube. It's called South Pole.
A number of neutrino telescopes detected those. That was quite a large flux of neutrinos.
Yeah. The Europeans have got a system called Antares, which is under the Mediterranean, off the coast of the south of France, but it's still in its experimental stage being set up. I don't think they've had much actual science data from it yet. It's a promising new field, though.
Yeah, the Japanese have neutrino telescopes, and there's others around the world.
The Russians do as well.
I don't have a complete list. I wish I did. I'll have to look that up and get it to you. So
well, the main detector, the most famous detector, is the one that is buried under the mountain in the northern Italy, the Gran Sasso mountain. It's deep underground. That's a detector, neutrino detector. It's been running for a number of years now, decades. So
they're doing a big dark matter search there as well, aren't they?
Yeah, now that one, well, all of them can basically detect astrophysical events, and also now they can get some idea of the energy spectrum for these things, so they can determine. And they're seeing these very high energy neutrinos. I'll have a link in the show notes to some of the most recent notes about the detection of those, and the very high energy neutrinos are a bit of a mystery. I used the M word, but they're a bit of a puzzle, I should say. And
I think it's clearly clear they're not coming from our sun.
Oh no, they're not.
From the sun.
They're coming from some deep astrophysical source that's not known yet.
I would guess that they're probably coming from supernova remnants.
Yes. Well, I mean, we don't really know. It haven't pinpointed a source. The thing was the cosmic rays, the high energy cosmic rays, their trajectories bend in the galactic magnetic field.
Right.
It's very difficult to trace them back to a source. But the neutrinos are not affected by magnetic field, so they should be telling us what a source is. So that's something that's going to get pretty exciting. I think we're just beginning to understand what we're going to learn from that. And so we're, there's these new windows opening up all the time. It started with visual light, and which is just a tiny fraction of the electromagnetic spectrum, and then we added radio, and when we got satellites, we started adding infrared and ultraviolet and gamma ray and X-ray, and we're now adding neutrinos and soon, hopefully, gravity waves, which are not electromagnetic at all. And we'll have all these new windows. Hopefully, the competition for funding won't be too intense between those different parts of the spectrum. That is, that's forever a problem with science, is getting enough money to build the instrument you want, and or to build the satellite that you want to fly the instrument. So anyway, I did want to mention one thing that is not that new, but because I had a bit of a personal connection to the paper, I wanted to mention, and I'll have a link in the show notes. And I thought of it when we mentioned the neutrinos from the supernova. Jim Franzen, from whom I took a quantum mechanics course once a few years ago, recently wrote a paper in which he found that gravitational fields can reduce the speed of light, but he calculated also they should not affect neutrino speeds, and he thought that was reflected, but possibly in the data from the neutrino arrival time versus the light curve of that particular supernova. It's a really interesting phenomenon. It's consistent with what's known about physics, where a photon from as it travels through space, will form a virtual pair of particles, which split up and recombine, and that actually slows light down very slightly, on average. And if it travels over hundreds of millions, or even just 1 million light years, you can see it. So I'll post a link to that. It's a bit esoteric, but I found Jim Franson to be a good teacher. I think that within this paper you'll find very clear, plain English explanations of what he's trying to do. Then you'll see the calculation, which is not so easy, but I'll put that up for you. It was just fun for me seeing something by Jim Franson. I know he's done a lot of work in quantum information, but now he's into he's dabbling in astrophysics. It's kind of fun. So what else have we got going on this week, guys?
Well, we're still.
Go on, Ciro.
No, go ahead, Adam. I'm sorry.
You sent me a link about naming a planet, exoplanet.
Yeah. Well, I was going to say that there was another discovery of an exoplanet actually this week that was reported. This one was it's Kepler 443b. It's a pretty interesting discovery. It's that it's also a circumbinary discovery. So obviously that means that the planet orbits two stars, a binary star system. This one also, one of the things that is unique is that the tilt of this particular planet changes constantly. So that makes the transit of the planet itself visible only 9% of the time.
Right.
So it was very kind of almost a chance discovery by Kepler, according to the to the report. So yeah, as we were saying earlier, there's always new surprises in the discovery of these exoplanets. So this was one story, and then the other story regarding exoplanets. I don't know if you guys have already reported it or not, since I came a little bit late on the show. It's the news that the International Astronomical Union has opened the vote to name 32 exoplanets to the public for the first time in the history of humankind, basically. So they have created a web portal, and these 32 exoplanets are in 20 star systems. So some of the star systems are composed by one single exoplanet, and some by 3 or 4, making up for a total of 32 of them. And they have a preset list of names that the public can choose from. Some have already started being criticized for the ridiculousness of them, but by and large, some other ones are pretty interesting, though. So I think that's kind of exciting, though, to give opportunity
What's
to the
that
public.
link? I saw that. What is that link? Forgot.
I do not have it in front of me right now, but I'll be more than happy to provide it to you guys, and maybe Paul can put it in the show notes
Sure.
if necessary.
Do you know the name of it? I could just Google it.
I could. It's if you search for naming exoplanet, International Astronomical Union, it's the IAU that opened it up. Something like New Worlds, or I forgot. I don't want to give the wrong name.
I saw some article about naming the planets a couple of times, and I didn't pay much attention because I heard about the ridiculous names or something. Besides, were they going to let them choose, or were they going to choose the names for them?
Yeah, I'm not quite sure exactly where the original selection came from. I haven't looked into that. Who originally selected the candidate names, but some are interesting. I don't know. Some are more interesting than others, I should say.
Yeah.
Name exoworld.iau.org.
There you go.
Okay. But I think giving them names will help a lot, because most of them are things like Ogle-2012-BLG-0536LB, which doesn't really connect with the public's imagination, right. Or HATS-14B, or HD 219134C.
What I find actually intriguing, I've said this to people before, just friends or just people on Google, just doing a hangout. It's interesting because we are on the precipice of literally creating a new chart, so to speak. And hating to use the Star Trek reference all the time, the point was that when they go out to seek out new life and they go to a planet, they already know something about this planet. They know the star. They have a name for it, and in other words, they're following a map that somebody hundreds of years before them created. And in a sense, we need to do that. Not that we're going to actually have warp drive to go do what they did, but the point is that we are doing that now. Instead of the old star charts from thousands of years ago till today, just plotting stars and naming the stars or just numbering them, we are now seeing exoplanets, exosolar systems, that we need to do that. We need to plot this. Over here is a star, such and such kind of star. Maybe it's a G7 star, and it has 5 planets that we know about around it. One of them seems to be in the habitable zone. In other words, that sort of categorization has just started. Before it was just the stars. Now it's like the M-class planet. They're being charted, and I think that's really interesting because sooner or later, in 100 years from now, who knows how long from now, sooner or later, we're going to need a map like this if we're going to, go there, or if we're going to try and send even probes there or something to that effect.
Yeah, well, I mean, a catalog like we have now would probably do just fine, but it's and astronomers have been making catalogs for about 200 years, but if you go into a good astronomy library, which I recommend doing at some point, and there's an old book, actually an old pair of books, or I think it's actually 2 or 3 volumes, called the Bonner durch Musterung, or the BD catalog, which was compiled in 1855, and it's still used, and it's exquisitely detailed information about stars in these catalogs that are going on 200 years old, and so the catalog is a time-honored way of letting us know it's there. I think, but mapping things and giving them names helps the public connect.
Right, absolutely. I completely agree with that. I was going to say that I think that it's pretty revolutionary that an organization that historically has been pretty much, I would say, close to the public and only available for people that were strictly in the field. We know the most famous example of the International Astronomical Union that everybody knows about is the example of the vote of Pluto, right?
Yeah.
When it was demoted. But now with the technology, with the availability of technology, I think it's revolutionary that this organization and the International Astronomical Union is not the only one, although it's probably one of the more stringent. Right, it's a pretty important organization. It's probably the mother of the astronomical organizations out there. They kind of dictate names, and they dictate taxonomy and all those things, right? So for them to be able to say to the public, here you go, I think it's an indication of what they are trying to do, and like you were saying, Paul, excite the public, in these sort of things.
Yeah, well, you notice that the science teams who are doing a particular mission, like the Pluto, the New Horizons science team, or the Curiosity science team, they will give unofficial names to a lot of objects or areas or regions that once they've given it that name, it's pretty well stuck, and the IAU pretty much can't do much about it.
Well, I mean, of course, these catalogs are absolutely beautiful, and of course we still need them, and we're going to continue to use them. What I'm basically saying is that now we're going back to these catalogs, and in addition to knowing everything about that star, what kind of star it is, its temperature, all this other stuff, exactly where it is, now we can go back to some of those stars and say, well, incidentally, this one also has, these planets around, orbiting it, and that one has, some strange planet orbit. In other words, we're going back to those catalogs. We can't dispense with those catalogs.
No.
But certainly we're going back to them now and adding this information about the planets orbiting these particular stars as we continue. And I think that's exciting, and it is a public thing too.
It's fascinating because, like you were saying, Patrick, there's some of these stars, some of the more famous ones. They've been known, some of them for thousands of years, literally. They've been discovered many, centuries ago. And now it's very exciting to be able to say, okay, that particular star that we knew the existence of already thousands and thousands of years ago. Now we know that there's another planet out there, right? There's another planet going around that star.
Exactly.
Almost, it's a brand new world, that's for sure. I mean, with the discovery of exoplanets, it's really a great era to be in right now, I think.
Yeah. By the way, if you want to get the exoplanet stats really fast, there's a really great site called exoplanet.eu. And it has a lot of information at your fingertips about exoplanets, and if you click on the diagrams tab, you can set up your own plots of different exoplanet characteristics. It's really cool. I've used it quite a bit.
Oh yeah.
Another one that I think is really good is Abel Mendez's site, the Planetary Habitability Lab. There he's focused on the Earth similar planets, and you can get the lowdown on the he keeps that very up to date, and you can learn which planets are most Earth-like and which planets have a high habitability rating. Now that's always in flux, always evolving, because people are starting to talk about exomoons and so forth, which we haven't detected yet. But if you assume that these big planets have moons, they might be habitable as well. So there's that will always be in flux. But I think that's if you want to just get the lowdown on, okay, what planets could possibly be kind of like Earth. Go to Abel Mendez's site, just Google Planetary Habitability Lab. It's at the University of Puerto Rico.
Yeah. It's absolutely excellent website. I at least once a week go to it myself, Paul, and just browse through it. There's a extremely well-made visualization and charts. There's something called the periodic table of exoplanets,
right,
which characterizes them by a number of different parameters that they have established, like habitability factors and sizes and so on and so forth. And and like you were saying, it's very well cured, and it's by experts.
Yeah. Abel Mendez is an expert on what they call the Earth Similarity Index.
Yeah.
Which he pioneered. Say again.
It's his invention, isn't it?
Yeah, it is. Abel, and he assigns an ESI to all planets that are, below a certain size, or above a certain, And now you'll notice that not a whole lot of Mars-sized planets have been discovered. If you go look through those catalogs, and the reason for that is discovery bias. Those are hard to detect. Even Venus-sized planets are hard to detect because of their size. Larger planets will be easier to detect. So we detected mostly hot Jupiters, and then it became. It wasn't until later that we really started to get a good cross section. but that's something that, ideally at some point we will have more data on the smaller planets as well. Something between Earth and Mars size. Right now we have very little information. And there's only a couple of planets, I think, that have been detected that are in that range.
I've got the PHL. Is that the one?
Yeah, the UPR.
Yeah.
PHL, the UPR, that EDU.
That EDU, yeah, I got it. Yeah, I've seen this before. This is pretty cool.
Yeah.
We got something like 31 total.
Now, those graphics they have on there, those are artist conceptions. we don't really have pictures.
As a matter of fact, I've actually got this photo on my hard drive. I like to share sometimes when I'm going to hang out. That photo of all those planets.
Yeah, that will change.
It's interesting because there was one of these, I forgot which one in particular that we just talked about. I believe it was the story that Adam was speaking of at the beginning. And I shared the post about the story with the artist conception. Now, mind you, I clearly marked at the bottom that the image was an artist conception. Yet there was a number of people that came to the post and they started claiming that you are putting this is not a photograph, this is Photoshop. Now, wait a moment now, I never said this was a photograph.
Yeah,
but there's always somebody that thinks that those are photographs.
Sometimes you can give the people all the information, and they'll look at you straight in the eye and swear that it's a conspiracy or something.
No, the thing about the images, it's some people criticize the fact that that there's some sort of an exciting image out there, but it could stir people away from the actual context of the story. But the image is obviously to attract the public, right? You want to put an image that is attractive, so that people are attracted by the story and they're going to read it. Otherwise, they're not going to be seeing the story in the first place. So,
yeah. I mean, the normal guys like us, we know that we know why artists' conceptions are used. We know that scientists love to hire the artists to do these things. And it's actually helpful, to have artisans, doing this.
Well, yeah.
But like I said, there's just some people that just don't get it. They just don't, they think, how do we know that's? How do I know it's not a Photoshop? Like I just told you, you can paint it.
You just have to preface it. We don't have any actual pictures of exoplanets.
Oh, we do.
Well, we have
little dots.
We have little dots, yes.
Yeah, we have little dots.
But the thing is that we are very visual human. We're visual beings. Humans are. So I mean, we're obviously attracted by imagery, by images, and the senses. This is our senses, right? Sound and sight, and so on and so forth. That's why we have beautiful animations and we have beautiful graphs and pictures.
And these artist conceptions will be getting better and better as we use new telescopes like the James W. Space Telescope to analyze the atmospheres if they can, and other telescopes they're going to be analyzing. Once we know what the atmosphere looks like or things like this nature, we can start basically telling these artists, we're thinking colors of of this color or that color, that sort of thing. In other words, they'll have a more scientific way to put it into their artwork.
The reality is that a lot of these celestial objects, and even if we just let's scale back down to the solar system now, right? A lot of the objects in the solar system are pretty unexciting. I mean, if you really want to look at it, right? Do we have a bunch of rocks out there?
What?
How dare you? That's blasphemy.
Well, no, I mean, no, but really.
Well, they look like potatoes with pot-marked potatoes. Right? Yeah.
If you are somebody that really, are looking for, people are looking for the imagery with colors. They look at the nebulas with a lot of color enhancement, and they look at the stars with a lot of color enhancements. I mean, those are the type of things that attract the average public, right? The one that is not going to worry about. They don't look for the story. They look for the pretty imagery. Right. But in a way, that's how you attract the public, and hopefully there's a percentage of the audience that is going to decide to go more in depth. Right?
Well, with the Juno mission that's on its way to Jupiter right now, the scientists didn't ask for a camera because that's not what they're studying. Right?
Yeah.
But they put a camera on that spacecraft.
Oh yeah.
And because they are going to get spectacular images.
Yeah.
Well, I mean, what I'm saying, is that we love space and we love the objects. I mean, there's people that like that stuff, like us, but there's a lot of people that do not like to look at a piece of rock. It's a reality, and you have to entice those folks. You have to go ahead and do something to excite them. And the only way to excite them is that you cannot excite them with a bunch of equations or mathematics. You can you can only excite them with some visuals,
right?
Some imagery.
Well, I mean, it even helps the scientists. I mean, when you think about, we're all humans are visual creatures. We all like to see pretty pictures.
Of course.
But if you take an artist and tell them, well, I think this planet, you give them some scientific data that might make this planet in such a way. The artist is going to take that information and draw what is accurate to the two people's idea.
Right.
But if you give them more scientific data, like I said, if you're going to analyze the atmosphere and stuff like that, then you can start actually thinking maybe it's not that color, maybe it's this color, that sort of thing.
Right.
So it's going to be more and more accurate, even though it's a painting, so to speak. It's going to be more possible that it's a real representation.
Right. But my point was that. Even though the Juno camera is there primarily to get the public excited about Jupiter science, I think they're going to get science out of that they are not expecting.
Yeah, I mean, if you go all that way, it's like going on vacation without your camera. I mean, you got to take a camera.
Well, I think there's something to be said for going on vacation without your camera, but
it's going to be handily placed for looking for water plumes coming from Europa for a start.
Well,
volcanic eruptions from Io.
Yeah.
I think mostly that what they'll be looking for will be in the atmosphere of Jupiter, but and Jupiter has a very beautiful atmosphere. It just there's all these exquisitely little detailed things that are very pretty to look at. But I think they're going to get science out of that. I think there's going to be people that really take it seriously, and so that's my prediction anyway. We'll see how it comes out.
I hope so. I mean, like I said, why would you go without a camera?
Well, their scientific objectives have nothing to do with looking at images. So they did not need a camera to do this mission. They're all about the orbiting close to Jupiter and studying the geophysics of Jupiter. The Jupiter physics.
Trying to work out what's inside its interior.
Yeah. And also its magnetic field and its, charged particles and all that. The kind of things that scientists get excited about, but the public doesn't care.
I'm just wondering. I'm just wondering if the electronics of that spacecraft are really going to survive. I mean, I know they built this thing like a tank because of Jupiter's radiation, and from what I understand, Jupiter's magnetic field is so strong it reaches the orbit of Saturn.
Well, I don't know about that, but
that's what I was reading.
It's a very strong field.
I mean, it literally reaches
the orbit. It has its own magnetic field.
But its radiation is pretty well characterized, and I think there's not going to be I think they're ready for it.
I think it flies on an elliptical orbit, so it doesn't spend a lot of time in the heavily irradiated part of Jupiter.
Yeah,
around Jupiter. It'll fly in and out of the radiation zone.
Well, they kept saying that Galileo is going to die any day now because the radiation here is so bad. And Galileo's hung in there indefinitely. It was, they really do over-design these things and then they're conservative about the environment, then they're conservative about the design, and the net effect of that is it's tougher than anybody could have thought.
If I understand it, this one is built like a tank.
It is.
Yeah. There's no point in sending a spacecraft all the way to Jupiter for it to break down within a day.
Oh, no, I'm sure it'll be fine. And the one thing about this spacecraft that's interesting that nobody would have thought of, 20 years ago is that it's getting to Jupiter with solar panels for power. The dogma was for a long time, you go past Mars, you can't use solar panels. and now we're going way, way past Mars and solar panels. And they did it by cutting the power demand way down and by building really big solar panels. That
also the solar panel technology is getting better.
It is better. It's not. I mean, it is better. Yeah. So the efficiency of the cells is around 30% now, which it didn't used to be anywhere near that. They're gallium germanium arsenide, whatever. Whereas they used to be just silicon. Yeah. So they are pretty efficient, and that helps a lot. And
there's not a lot of plutonium about either, is there, to make radioactive powered?
No, the radioisotope thermal generators are hard to do and very expensive, and so they traded it off. They thought, well, okay, it's possible we could do one, but boy, that would cost a lot of money and take a lot of time. And
they have just so much left. They have enough to do that, but they want to make sure they use it for missions that really need it.
Yeah, well, they found a way to do without it, and so they're it's kind of a heroic measure, but they did it. So I'm pretty proud of those guys. It was not an easy thing to put forth. Hey, let's use solar power Jupiter, because a lot of people would just go, what are you talking about?
There was an interesting paper interesting news coming from NASA's Marshall Center this week about a light sail project. NASA has given a grant to these guys to look at building a light sail craft that will head out to the heliosphere, the edge of the solar system, in around 10 years, they reckon, which is pretty impressive, given that that's twice the distance of Jupiter.
Yeah, I'm skeptical that we're really ready to do that with a solar sail, but
it would be a tiny, tiny spacecraft attached to a huge solar sail. It would have to be.
Yeah, I agree with that. But in terms of what's been demonstrated so far, not much.
Well, no.
And
I think it's a promising technology.
I mean, in terms of the physics of it works. I mean, but you have to get the sail deployed and get it under control. And
the Planetary Society had a prototype, didn't they, this year?
Yes, they did, and they were successful with that after some a couple of difficult weeks.
You got difficulties,
yeah, but
they had their difficulties, but
considering how cheap it was, that's not too surprising.
The launch was beautiful. I was at the launch.
Yeah,
it was publicly crowdfunded, wasn't it? Basically.
Yeah. Well, I mean, I think I threw a few bucks at it myself, but
yeah,
it's
good. It was considered a test flight, though. It was considered a test flight. So in a way, the glitches were. I'm not saying that they were, necessarily welcome, but the intent of the flight was to find out what went wrong.
Yeah, well, I've seen much more expensive hardware also have problems. So
the Planetary Society don't have the resources that NASA do they?
No. But they did okay. They did get it deployed, and
I think most of the problems seem to be in communication with the spacecraft.
Yeah.
They have difficulty knowing whether the solar sail has been deployed. They were having to wait for it to orbit the Earth, come around to be in range of, I think, the Goldstone radar station that was tracking it. And it kept moving in and out of range of the antennae, things like that. NASA would probably be a lot better at launching such a craft.
But the cost would be 2 orders of magnitude higher.
But they'd be able to track it a lot easier, wouldn't they?
Sure. Well, I mean, that part would probably work better. Yeah, I'm sure it would. But the thing is, if you can get it to work at all, then you win. And they did. They got it to work. So it was painful and stressful, but they got it to work.
I've been impressed with Dawn's ion propulsion system. Dawn spacecraft. Series. That's another really promising form of propulsion.
Yeah, well, I think ion is actually pretty mature. There's a lot of spacecraft flying ion engines now. And you'll see a lot more of it. Actually, the geosynchronous communication satellites are pretty much all migrated to all ion because of the weight savings that they get. And so you'll see more of that. And so it's a mature technology with you can buy Hall thrusters or you can buy ion thrusters. They both basically use xenon fuel, but you can use other types of fuel. There's argon, and there's a number of trade-offs you can make. The problem with that, of course, is like anything else, it's power. You need power to run those things. And if you want them to run at high efficiency, you've got to accept a low thrust. And so the Dawn mission was designed to take a very patient approach to getting out there and rendezvousing, and it worked.
Yeah, there's nothing wrong with that.
Yeah. But there was a British moon mission a number of years ago that used ion engines to make a very slow rendezvous with the moon, and it worked. So you just have to be patient and have plenty of time. Once you have that, an ion engine can get you there very efficiently in terms of mass.
What is Dawn doing right now, anyway?
It's orbiting Ceres.
Yeah.
Oh, that's right.
It's actually lowering its orbit.
Yeah, it's spiraling down to its lowest mapping orbit.
That's right. I can't remember which way was Dawn going.
We'll get a lot more. We'll get a lot more images soon once it's done lowering the orbit.
It's getting closer to the alien city.
to the pyramids. I want to see the pyramids.
It's a lot more interesting than anyone thought it was going to be. Ceres.
Yeah.
Stuff on the surface of Ceres. Not just a rock, a boring rock. It's got bright spots.
Right.
It's got a pyramid. 4-mile high pyramid.
It's a mirror.
Well, yeah, I found a number of people wrong on the internet this week. They were saying it was it was a glowing pyramid, which
I go. It's got streaks on it. It's got white streaks.
The white streaks. Yeah.
I think that the latest thing was that it was probably salty substances or even like a something that like maybe an asteroid or not an asteroid but a small meteor or something got hit and it uncovered some of the lighter material underneath, which could be snow, it could be salty snow, it could be things like that.
Simon is still on ice.
Yeah, I think we still don't know what those mountains are.
By the way, I don't know what the fascination is with the pyramids that humans have. I mean, it's not even a pyramid anyway, right?
No, it's not a
pyramid.
It's a mountain of some kind.
That's one of those key words, right? They mention the word pyramid, and everybody goes ballistic.
Well, okay, sorry, no, Ciro, you forgot. It's the mysterious pyramids.
Mysterious pyramid.
You have to say mysterious.
See, that was last week's podcast. We were talking about education and the lack thereof in science.
Yeah, and mystery mongering on the media. Yeah, yeah. I mean, it is a mystery, strictly speaking. But when people start using the word mystery, it's clickbait. So,
but I mean, but it's fascinating, though. I mean,
it is. Yeah.
I mean, I guess scientists could call it a mystery, right?
Well, they could, and they would be right. But
right.
The problem is the connotations.
The connotations, exactly.
Yeah. It is a mystery, strictly speaking, and I don't think anybody knows what that big mountain is doing there. It just doesn't make sense.
Well, did you know what's happening with the new trend of these science shows, which some of them are very well made, and I watch a few of them when I have the time. On the Discovery Channel and the Science Channel, they got this trend of using the word alien everywhere. Alien planets, the alien galaxy.
It's alien world.
The alien star. I mean, it's really used me and my wife were watching a show a couple of weeks ago, and it must have been 100 times during the show that they mentioned the word alien. I mean, literally every sentence or every other sentence, they were injecting the word alien, and I'm like, what's going on?
Well,
strange.
Okay, well, you just tell me the title of this podcast has to have the word alien in it.
No, but it's interesting to see how they play the human psyche, though. A lot of these shows,
Well, we are fascinated with others that are not us, right?
Right.
Sort of a combination of fear and fascination.
It is.
But I mean, I am fascinated. I mean,
it's an alien world. It's not. It's not from here, so it's alien to us.
Right. Exactly. Well, the point is not the use of the word for the sake of using it. The point is the abuse of the word. The point is that the exploitation of the term, I guess, is what I'm trying to say. You know what I mean?
Well, that show on History Channel, Ancient Aliens, has been very popular. Right?
That's another story altogether.
Yeah, it doesn't have anything to do with science, but
right, exactly.
It's
or history for that matter.
It's one big long fallacy.
It's speculative. It's a huge speculative show.
Well, if it were just speculative, I have no problem. But the fact that
it's not just speculative,
it's fallacious. It's this sort of fallacy of incredulity, right? I can't figure out how ancient man did it. It must have been aliens.
Right. Exactly.
Yeah. It's and the argument from ignorance. So it's an exercise in logical fallacies. It should
exercise in logical fallacies. I'm going to use that.
It's been criticized. There was a
and bad hair.
Oh yeah. But if nothing else, has served the purpose of entertaining millions of internet users.
Yes,
But the problem, though, on the serious side of, on a serious note, though, the problem is that there's a lot of people that do not understand, the distinction and the lines and what is really science and what is not, and what is portrayed as science. That's one of the problems with these sort of shows.
Right. Well, yeah. I mean that's there's no copyright on the word science, and anybody can use it anytime they want to mean anything. I posted something today on Twitter about a guy who does alien abduction studies and claims that he's a scientist, and all the evidence shows that he's not much of a scientist at all. But and he's convinced that their human alien hybrids are on the planet and they have evil intentions and all that. But on his website or somewhere, he said, my priority is rigorous science. But and he can say that legally. People have to learn not to believe it.
Yeah.
So, I think we're going to wrap up here pretty soon. We've been going on for a while. So I think what we'll do is I wanted to let everybody know that thanks to Adam's efforts, next week we have Pamela Gay lined up to be on the show. And if you have questions about astronomy or about science communication or about astronomy communication, get them to us any way you can. You can email them to unseenpodcast@gmail.com. That's one way. You can also go onto our subreddit, the Unseen Listeners, or you can, tweet them to me. I'm at Paul D. Carr, and there's also an Podcast Unseen Twitter account. We certainly want to hear from you, and we'll have lots of questions for Dr. Gay, but if you have questions, let's get them out before her, give her a chance to answer them. We had a good set of questions for Brian Coberline, didn't get to all of them. So this is, I'd like to have a similar long list of questions for her. And and if you can ask her about what it's like to be a woman scientist, if you want. So I'd love to hear from some young women who are thinking about doing it themselves and wanted to ask her about it. So anyway, And by the way, if you are a young woman who wants to be a scientist, I know at least 4 guys who will treat you very well and want to ask you serious questions. And so, anyway, let's go around the table one more time and get everybody to say one last thing. Adam, you did a lot of good research for the show. Thank you. And any last words?
It's been a pleasure as usual. I love talking about planets and space and astronomy. It's been a pleasure to talk to you guys as usual.
Okay, get back to bed. It's what is it? It's almost 5 in the morning out there.
It is, yeah.
Okay, probably too late to go back to bed. Ciro, Villa.
Yes, glad to be here, Paul. And I think that next week's show is going to be definitely one not to miss. Dr. Pamela Gay. I've known Dr. Gay for a long time, and and I'm really happy that Adam was able to snatch her, so to speak, for the show. So definitely looking forward to that one.
Yeah, it's a coup. I didn't think we'd get her. Okay, Patrick.
That's pretty pleased.
I just want to thank the 3 of you for getting her on, and I thank you again for making me part of this podcast. I'm the sort of the low guy on the totem pole here, but I certainly enjoy every one of these podcasts, especially when we have special guests. You're talking about Pamela Gay, and I'll definitely try not to be late for that one. And I certainly want to ask her, about the woman in science and see what she has to say. I know she's pretty outspoken about it. Last time I heard her say something about one of the old guys. In any case, thank you again, and hopefully I'll be on time next week.
Okay, well, thanks everybody. Now, as I mentioned, we'd love to hear from you. So if you have questions, comments, criticism, cliches, please show up. Come to the blog at unseenpodcast.com, and you can comment right directly on the blog entry for this episode, which should be episode 19. I haven't got a title yet, but I'm sure it'll have the word alien in it somewhere. If this is an open participation contest, if you'd like to be on one of the panels, and you like talking about things like astronomy, space, the future of humanity, technology, aliens, by all means, send me an email at unseenpodcast@gmail.com, and we'll set you up. And everybody, I'd like to thank, again, Adam Synergy Smith, Ciro Villa, Patrick Festa, and again, check us out at unseenpodcast.com. And we'll see you next week in episode 20 with Dr. Pamela Gay. Good night.
Bye.
Good night, everyone.
Good night, everyone.